Our group received a Hall effect sensor for our Beast project, and we decided to recreate our own version of the Tower of Terror from Disneyland. It uses a Hall effect sensor and a magnet array attached to a spinning drum to create a rotary encoder that senses movement. We also utilized a motor and control circuitry to create movement.
Everything starts in heart. Power supply. Power supply provides volts to the Arduino, the H-bridge, and the board. We'll get to what the board is in a minute. We go to the magnet. The magnet is the heart of our thing because we are using a Hall sensor which detects magnetic fields. And in this case, it's receiving a transitioning magnetic field. Why is it transitioning? We'll get to that in a second.
We used our Hall sensor to create a rotary encoder, which picks up a signal from an array of magnets with alternating fields. This creates a sinusoidal waveform, which we can use to determine the number of pulses that is experienced by the elevator. This is done by reading the peaks. If we know the number of pulses per revolution, and we know the diameter of the drive wheel, then we can determine the linear distance traveled by the elevator in the shaft.
The Hall effect sensor then sends a signal to the board, which also in turn powers the Hall effect sensor, but that signal that goes to the board is then translated into steps by some weird, funky space electrician magic. Tim knows. Ask him.
So I'm not Tim, but I'm going to give this a shot. This board that we're talking about is a dual op-amp comparator circuit. This interprets the waveform that we get from our Hall effects. So we're taking in a voltage and we're going to compare it against two set voltages. These are set by these potentiometers, and they're going to clip our sinusoidal waveform into two square waves, a high and a low output. So any transition from high to low indicates that there's been one pulse detected by our system. This board makes it easier for our Arduino to interpret the waveform coming out of the Hall sensor, so we don't have to worry about having too high of a sampling frequency for the board.
Following from those steps, those go to the Arduino. The Arduino receives logic from the code in the form of logic, ones and zeros.
This is a general run over of the code. These are the variables that relate to the pins on the Arduino. This one is a holdover. And these are the levels of the elevator. And these are how the elevator slash sensor sees what pulse it's on and what it needs to do with that information. Now the first thing we do is set up. The initialize elevator is also used for a crash situation, so it made sense to make it into an actual function. Now, it sets all your variables to where they need to be, and the targeted position is set to a value of pretty much level 1 plus 2, just to help with calibration a bit. Now, what this will do is, while the limit switch is 0, which is both our stop and restart, and also the way we calibrate it and zero it, is that it'll print tramming, and it'll go all the way down to the limit switch until it stops, which once the limit switch is stopped or is down, the motor stops, it delays a bit, and then it sets the tramming and then tram movement, and then after that it goes to the move elevator loop, which the move elevator loop essentially makes sure that if it's either hasn't crashed or it's within tram, it'll try to get it to the pulse position within 0.5 pulses. And the idea is there's always a way of getting out when it crashes, but primarily this is using pulse and targeted position in order to dictate whether it goes up or down. Speed is set by position compared to where it needs to go. And then we also have some limiters, especially relating to going down, since gravity doesn't help a whole lot when you're trying to make things a little bit more controlled. But overall, that's how this section of the code works. And there's motor movement right here, which is another loop within that, and within other loops that essentially uses the speed and writes to the pins that they need to go up and down. It's how the PWM loop works. And then after all that, we'll return back to the actual main loop, which essentially what it's doing is it's constantly just generating random speed, like random travel times we need to meet, random wait times, and then a random level each time we want to go to, because we want to randomize it, make it more exciting, make it more fun to look at. You might be wondering what's with this right here. That's calculations to go from inches to revolutions and pulses. That's what we need to calculate it in, since it's 20 magnets per rev. Other than that, if it ever crashes, essentially it goes all the way down here. It stops everything, delays it, and that just in case somebody just needs to shut it off completely, and then goes back to the initialize elevator command, which everything starts over.
This then tells the Arduino what signal to use to control the H bridge, because the Arduino sends control to the H bridge. The H bridge then knows with the volts and the control how much to move the motor, which then powers the motor, and the motor creates movement.
An H-bridge is a collection of 4 MOSFETs which are arranged in an H configuration. It provides bidirectional control for the motor and uses pulse width modulation to control the speed at which the motor turns. So pulse width modulation varies the frequency at which power is allowed to pass to the motor. It's basically like turning the motor on and off again at a very high frequency, or low, and depending on the speed at which you want to move the motor. We use this to vary the speed at which the motor drives the drive pulley and moves our elevator up and down. This is randomly selected by the Arduino code to give us varying speeds at which the elevator will move from floor to floor.
This motor then rotates the pulley. The pulley wheel is important because the pulley wheel spins.
We decided on a split design for our pulley. We were going to originally use a wrap design that would rely on friction, but we realized that we'd probably have slippage that would limit the accuracy of our system. So we have 2 parts that come together, and the wire or cable passes through them and is secured in the center with a set screw. This allows us to keep one continuous length of cable and not have 2 separate parts. We designed the drum in such a way that each side, top and bottom of the elevator shaft will have its own drum that it spools onto. So when the elevator goes up, one side's going to spool up and the other side's going to spool out. And when it goes down, it'll be inverse. This keeps constant tension in the system, and we don't have to worry about cables slipping or jumping.
The pulley then creates controlled linear motion in the form of the cart. That is our measured value.
Mm-hmm.
That actually says measured, believe it or not. I can barely read it, I'm sure you can. That measured value then tells us where the elevator is. Now you might be wondering, how do we know where we start? Well, we have a limit switch for that. And that limit switch is plugged directly into the Arduino. That's a 0. It gives the Arduino a 0 to tell us where we're at. And then the code is like, oh boy, we know where we're at. And then it sends the logic to move the elevator. Now where do we decide where to go? We established floors. Those floors, I think we have 5 of them. I might be wrong. But as we go up and down, we know which floor we're at because we see the spinning of the magnet, which then translates to the Hall sensor in the form of a signal, which then goes to the board and then goes from steps from the board to the Arduino. And that tells the Arduino where we're at.